My name is Joseph Lynch, and today I'll be talking about how Netflix ensures highly reliable online stateful systems. I'm a principal software engineer at Netflix working on our data platform. I work on essentially every kind of online system that stores state that you can imagine. If it stores data, I probably work with it. I'm an Apache Cassandra committer, and I've worked across multiple different storage engines over many years. And today I'd like to talk to you about making stateful systems reliable. But to do that, first I want to define what does that even mean? Because I think that if you asked people, they might say something like, well, it means you have a lot of nines, right? Like, who's heard that before? If you have a lot of nines, you're highly reliable. Well, I think that your customers probably don't care a whole lot about how many nines your data store has. Instead, I think that they care, do the read and write operations succeed with the expected consistency model, so the semantics, within the designated latency, service level objectives or goals, always. A reliable stateful system has these properties. So instead of asking how many nines do I have, instead ask how often do my systems fail? When they fail, how large is the blast radius? And then finally, how long does it take us to recover from an outage? And then you're going to spend money to make these go to zero. Either you're going to over-provision computers, you're going to pay a cloud provider to solve these problems for you, or you're going to employ engineers to build cool resiliency techniques. But either way, this is the way that you make stateful systems reliable. And to kind of drive this point home of why nines are insufficient, I want to consider three hypothetical stateful services. They all have equal number of nines. The first service fails just a little bit all the time. It never recovers. And maybe we need to invest in request hedging or improving our tests to cover some bug. Service B occasionally fails cataclysmically. And when service B fails, it recovers quickly, but it still has a near 100% outage during that period. Perhaps we need to invest in load shedding or back pressure techniques. And finally, service C rarely fails, but when it does fail, it fails for a really long time. Maybe we didn't detect the issue. Maybe we need better alerting or failover support. Or perhaps you don't care about that service, and if it fails rarely, you'll just bulkhead it from the rest of your system and be okay with it. The point that I'm trying to make is that different failure modes in your stateful services require different solutions. And throughout the rest of this talk, we'll be exploring a multitude of techniques that we can use to try to make these properties go the direction that we want. So we want less failure. When we do fail, we want to recover quickly, and we want to minimize the impact. And at Netflix, we use these techniques to reach very high scales of online stateful services. We have near caches, which live near to service hosts that handle billions of requests per second in sub-100 microsecond latency. We have remote caches based on Memcache that handles tens of millions of requests per second in 100 microsecond SLO targets, storing petabytes of data. And then finally, the stateful databases under all of it is Apache Cassandra running in full 4-region active mode. In-region read-to-write consistency, single-digit millisecond latency. We serve almost the entire planet except for a couple of places, and we replicate our user state to 4 Amazon regions. This is a full active topology, and our video metadata is replicated even more. Like if you actually look at like the OpenConnect CDN, it replicates state to hundreds of points of presence across the globe. But we're going to focus in this talk on the AWS control plane that runs in those 4 Amazon regions. And today we're going to combine 3 different chapters. We're going to see how we build reliable stateful servers, how we pair those with reliable stateful clients, and then finally, how we can design our APIs to use all of those reliability techniques. So let's get started. We're going to cover 5 concepts in stateful servers. We're going to talk about sharding, capacity planning, rapid responses via rapid upgrades, and then 2 techniques we can use to use caching to improve our reliability. First and most fundamental at Netflix is that our applications do not share caches or data stores. My team, the data platform team, provides a managed experience where developers can spin up and spin down data stores on demand as they need them. We appropriately size them for each use case. And we can kind of see, let's go back to that measurement technique. Before, when we had single multi-tenant data stores that served multiple customers, we had rare failures that had large blast impact. When we move to this technique, we now have more frequent failures, but they have more isolated blast radius. So you can see that already we're making some trade-offs amongst those metrics that are appropriate for our business. But we don't want things to fail, so we want to make sure that each of these single tenant data stores is appropriately provisioned. And that starts with capacity planning. It starts with understanding your hardware. For example, here we've characterized 2 EC2 instances, and we've measured how quickly their disks can respond to real workloads. This is because less reliable disks, slower disks, mean less reliable service. These are the foundations. This is the level of detail you have to go down to in order to build up to a proper capacity model in order to minimize outages. So for example, that little latency blip there on the P99 of that drive, that's no good. You're going to have SLO busters there. But we have to combine this understanding of hardware with an understanding of our software. And we program workload models, per workload capacity models, which take into account a bunch of parameters about your workload, such as how many reads per second or how large those reads are. And then we can use some fancy statistics, or as a previous speaker said, a model that's good enough, I think, a good enough model, to output a cluster of computers that we call the least regretful choice. And when we provision that cluster, we're making a couple of trade-offs. And one of the ones that I want to call out in particular is that when we provision tier 3 data stores, we run those a lot hotter. We essentially save money on our tier 3s and our tier 2s, and then we spend it on our tier 0s. So our tier 0 data stores are over-provisioned relative to our expected workload. And this kind of automatic capacity planning that we can continuously run on our database fleet allows us to shift risk around and save money on one part of our fleet and spend it to get reliability on another. This also allows us to then take that cluster and replicate it to 12 Amazon availability zones spread across 4 regions. And we do this for a few reasons, but one of the most important ones is that we want to ensure that all of our microservices have local zone access to their data. Because as we'll see throughout this talk, if you can keep no network connection, that's the best. No network communication, most reliable. If you have to make a network call, make it in your local zone. If you have to cross zones, keep it in your region. And then finally, sometimes you do have to go across region. But also this allows us to have very highly reliable writes and read operations because we can use quorums to accept writes in any region. So by having 3 copies in every region, we are able to provide a very high level of reliability. This minimizes the times that there are outages. But sometimes we have to fill over. So this is a little diagram that shows the running Netflix system. And at least at Netflix, most of our money is spent on our stateless services. We actually don't spend as much money on our stateful services as we do on our stateless ones. And they're provisioned typically to handle around x/4 of global traffic. And then when US East 1 fails, because it's US East 1, we have to fail out of that region. And at Netflix, our resiliency team has built an amazing capability to evacuate an Amazon region in single-digit minutes. We can have all of the traffic out of that region. But that's a problem for your data stores because they have to be ready to absorb a 33% hit of new traffic instantaneously. And that's even a problem for your stateless services because they can't auto-scale that fast. So you have to reserve headroom. And specifically with this architecture, you have to reserve 33% headroom. But this actually is pretty okay because the alternative where we shard our databases and we run 2 copies instead of 4, in that alternative, we have to reserve a lot more headroom. Specifically, we have to reserve 100% headroom. We have to pre-buy a lot more reserved instances from Amazon for our stateless, and we have to run continuously a lot more for our stateful if we were to copy the data less. So this might not match your business, but at least in Netflix's case, paying that money to replicate the state is actually worth it, both in terms of reliability and because we can recoup the cost on stateless. But sometimes, even with all this capacity planning and sharding, bad things happen. And when they do, you want to be able to deploy software and hardware quickly. I don't know about y'all, but at least for me, a lot of the reliability issues happen because of software that we write. So we've carved mutation seams into our stateful images to allow us to more rapidly change software that doesn't affect the availability of the system. Specifically, we've factored it into 3 components. We have the components in yellow, which we change frequently. They're software that we write, like configuration agents or monitoring agents. We change them frequently, but they do not affect the availability of the data store because we don't have to bring down the Cassandra process or the memcache process or what have you in order to change these. So there's no reliability impact. We can change these quite quickly. We couple the stateful process and the OS kernel together. Because if we have to upgrade, for example, Linux, we're going to have to bring down the data store image. And when we do that, we're taking a risk. Because remember earlier I talked about quorums. If we take down one member of the quorum, we're running a risk. We could go down. So we want to do this as fast as possible. And we've released both a blog post as well as I've given a talk in the past about how we're able to do this in mere minutes, going from one EC2 AMI to another atomically. Similar to like a live CD or Pixie boot. And then finally, we have the state. And this is the most problematic part of a stateful service. And you don't want to touch it that often. If you have to move state around, you're going to have low reliability. Why is that? Well, one reason is because of the bathtub curve. Every time that we move state to a new instance, we're taking a chance that that instance will fail young. The bathtub curve refers to hardware typically fails young and old. So we really, if we've got a good, reliable database host, we really want to hold on to it. We don't want to let go of it. But if we do have to do that, we want to move the state as fast as possible. At Netflix, we use snapshot restoration, where we suck down backups from S3 as fast as humanly possible onto new instances, and then we just share the deltas as we switch over. This does have a major reliability impact. Before I get though to how we can minimize some of that reliability impact, I want to talk about monitoring. Because when you have stateful services, you have to care about how your drives are doing. At Netflix, when we're launching those new instances, I mentioned the bathtub curve. Well, we're going to burn in the disks, and we're going to make sure that they can handle the type of load that we're going to put on them. We call this pre-flight checks. Essentially, it's like a little checklist of like, can I talk to the network? Can I talk to the disk? Is the disk capable of responding in under a millisecond? And then continuously, we're monitoring errors and latency. These systems of monitoring throw away thousands of EC2 instances in our fleet every year. And why might I do that? Well, because these things are just pending reliability problems. If your drive is degrading, it's going to fail. If a drive fails, you're going to have a bad day. It would be better to get off of it earlier. But that doesn't just apply to your hardware. It also applies to your software. Who here has had a Java program go into an endless garbage collection death spiral? Come on, it can't just be me. Okay, a couple more. At Netflix, because we run so many JVM data stores like Elasticsearch and Cassandra, we run into what we call queries of death fairly frequently. So what we did was we attached a monitoring agent to every JVM in our stateful fleet. And that monitoring agent detects this condition within about 2 seconds. So if our JVMs enter this death spiral, it immediately takes a heap dump, puts it in S3 so that we can analyze it later, and remediates the incident. It kills the process. In practice, this reduced 2,000 plus SLO violations at Netflix in the first year that we deployed it. Because over the course of a year, when you have 2,000 plus clusters, bad stuff happens. So you want to recover quickly. And little agents like this aren't hard to add to your processes. But let's say that we've invested in all these things, and even then, we still have to be careful how quickly we do maintenance. So in the x-axis of this graph, we have how often we do maintenance on the Cassandra fleet. In the gray box, there are some parameters of this simulation, 2,000 clusters, between 12 and 192 nodes. And on the y-axis, we have how many outages we expect to cause through our maintenance. So we can see using the naive data streaming approach where we move state between instances, we can only really do about quarterly maintenance before we start accepting more than one outage related to this maintenance per year. In contrast, if we can send data faster, then we can get to monthly maintenance. We're able to image our fleet even faster without causing too many outages. If we decouple compute from state and use EBS volumes and execute state movements with EBS swaps, we can get even farther. But ultimately, to get to something like weekly level changes or being able to roll out software changes faster, we need to use that in-place imaging technique that I talked about earlier. As far as I'm aware, this is like the best way to do this. I'm super curious if anybody has other ways. But at Netflix, we've kind of taken this journey, starting at the red and then over time moving to the green so that we can recover faster from software issues. Next, I'd like to talk about caching. Because at Netflix, we kind of treat caches like these materialized view engines. So services, if you think about it, they're really performing complicated, almost joins, right? Like they're talking to multiple data stores, they're running business logic, and they have some output of that computation. That output, at least at Netflix, doesn't change that often. So we put it in a cache, and then most read operations hit that cached view. Whenever the underlying data of that service changes, the service recalculates the cached value and fills that cache. Now, some of you, I hear what you're saying. You're going, oh no, the cache could go down. the slide isn't actually relevant to that. The cache could go down. That is true. However, at Netflix, we've invested in making our caches highly reliable. For example, investing in things like cache warming. So if a node fails, we repopulate it with the cache data before it goes into service. And by replicating it to every availability zone. So if clients miss in one zone, they can retry against another. So in practice, these caches are essentially your service at that point. And Memcache can handle orders of magnitude more traffic than a Java service can. One anti-pattern that we discourage is putting caches in front of data stores. Instead, we prefer to put them in front of the service, because a cache in front of the service protects the service, which is, at least for us, usually the thing that fails first. The cache is cheap relative to the service, and like I mentioned earlier, stateless apps are quite expensive to operate. So this technique can help us improve reliability by decreasing the amount of load that the data stores have to handle. It does shift load to caches, but like I mentioned, those are easier to make reliable. We can actually take this technique even further and move all the data into the client. We call this total near caching. Netflix has written a series of blog posts about this, as well as an open source project called Hollow. And the way this works is that the source of truth data store isn't even involved in the read path. All that it does is publish a snapshot up to some blob store like S3 through the producer. And then the video metadata service in this case starts applying the delta to the in-memory dataset that it has, and then can atomically swap over from version 1 of the dataset to version 2. At Netflix, we like to treat Hollow almost like Git, but for your configuration data. And this is the service that can handle billions of requests per second because there is no network call. It's all local to in-memory. It's great. The more things that you can fit in this, the better. All right, so we've seen a number of techniques for how to make reliable stateful servers. But none of those are any use if your clients are doing the wrong things. So let's dive in to how to make reliable stateful clients. And we're going to cover 6 concepts. We're going to talk about signaling, service level objectives per namespace and access pattern, hedged requests, exponential backoff, load unbalancing, and concurrency limits. So let's start with signals. Because at Netflix, there historically was a big debate about like tuning the timeouts and client tuning. And what we realized on stateful services was that you can't really set the correct timeout. Instead, you need to know who the client is, what shard of what data store they're talking to, and what data they're trying to access. And then from those, you can deduce the service level objectives. So in this example, at the top box, we have a client that's saying, hey, I'd like to talk to the key value service, the Napa shard of that service, and US East 1. And in the bottom, we're talking to a time series abstraction hosting a totally different shard. And those signals start returning information to the client. For example, they might tell the client, I'd like you to chunk large payloads. Large payloads are really hard to make reliable because you don't know, is the network slow or is it like dropping packets? It's difficult when you're transmitting multi-megabytes of data at once to know if it's latency or expected. In contrast, if the client chunks information into smaller pieces of work, you can individually retry and hedge those individual pieces of work, and you can make progress in parallel. But you can also go further and just compress stuff. So at Netflix, we've used LZ4 compression from our stateful clients to compress large payloads before they're sent. In practice, this reduces bytes sent by between 2 and 3x. And fewer bytes is more reliable. Why? Because every packet you send is an opportunity for a 200 millisecond SLO buster when the Linux kernel waits a minimum of 200 milliseconds to retry that packet. So if you can send fewer bytes, you're going to have more reliability. Compression helps you with that. It also adds useful things like checksumming and other useful properties. Finally, I want to talk about SLOs. Because in that signals endpoint, the services, the key value service on the left and the time series service on the right, are going to communicate with the client, this is what I think your target service level objective should be, and this is what the maximum should be. You can think of target as like the number that we're going to use hedges and retries to try to hit, and then max is like, after this, just time out and go away. We're also going to communicate the current concurrency limits. So the server is saying, hey client, you're allowed to hedge 50 concurrent requests against me, you're allowed to send 1,000 normal requests. If you're interested about hedge requests, I highly recommend a wonderful article from Justine at Google called The Tail at Scale. The general gist is that you send the request multiple times, and whoever answers first, you take earlier. But we can also tune these SLOs based on the particular namespace they're trying to access. For example, in this case, we have 2 namespaces that are actually pointing at the same data. But one of them preserves or presents eventual consistency, and the other one presents read or write consistency. Eventual consistency can have a sub-millisecond latency SLO. it's really hard to make a read-your-writes consistency model sub-millisecond. So the SLO on the left can be stronger than the SLO on the right. But it actually gets a little more complicated. It's not just the namespace. It's also the client and their observed average latency. For example, if we have client A and they're making GET requests against namespace 1, if they're observing 1 millisecond of latency, then that means that in order to hit the SLO of 10 milliseconds, we're going to have to send a hedge around 9 milliseconds. The same client might be doing put requests, and those are averaging 1.5 milliseconds. So we have to hedge a little bit earlier if we want to try to hit that 10 millisecond SLO. On the other hand, scan requests are real slow. They have an SLO of around 100 milliseconds. So we don't want to hedge until 77 milliseconds after that. And finally, client B might continuously be getting above the SLO latency, in which case hedging isn't going to help you. Hedging is just a strategy to help you meet the SLO. If you're always missing the SLO, there's no point in doubling the load to your backend just to try to meet something that you will fail at. And this leads to what I call kind of the 3 zones of dynamic hedging timeouts. The first zone is the zone of hope. This is the part where the client is observing latencies that are significantly under the SLO, specifically under half. Once you get to half, though, you're now hedging 50% of your work, roughly. So this is the part where you have to make a decision. You could either really try hard to make the SLO. This is the zone of last-ditch attempts. You could try really hard to make the SLO, in which case you're going to be provisioning your backend for 50+% extra load. Or you could just say, like, let's back off a bit and give the backend some room. At Netflix, when we hit the SLO itself, we back off entirely. And this is because, at least for us, when the backend service is on average above your SLO, there's probably something wrong, and hedges probably aren't going to help you out. So you can see that in these 3 zones, we need to use different approaches to how we hedge against the downstream services, depending on whether we're likely to get a positive result. We also have to be really careful when we're hedging requests, and we have to use concurrency limiting to prevent too much load going to our backend services. So let's walk through an example. In this case, client 1 sends 2 requests to server 1, which immediately goes into garbage collection pause because it's Java. At that point, client 1 weights the SLO minus the average and then says, OK, I'd like to hedge against server 2. Maybe it'll respond to me. At that point, it puts a hedge limiter in place. That 50 number we saw earlier, in this example, it's 1. We're allowing 1 outstanding hedge. When the client 1 tries to hedge request B, instead of allowing that hedge to go through, we say, there might be something wrong with the backend. Let's just wait for it. Once we get the response back from server 2 to request A, now the hedge limiter lifts. And a subsequent put from client 1 to server 1 is allowed to speculate. So we can see in this example, if we had done nothing, all 3 of these requests would have hit that latency busting 24 millisecond GC pause. Because of this hedging system, we were able to rescue two requests, 2 of 3. So this kind of goes back to that. In this case, we couldn't prevent the issue. We did have some SLO violation, but we minimized the impact. Fewer requests violated the SLO. We can use similar techniques to make GC-tolerant timeouts. So if I'm implementing a naive timeout, I might set a single asynchronous future at 500 milliseconds, and then at the end of 500 milliseconds, I throw an exception. In our stateful clients, we use what we call GC-tolerant timers, which is where we chain 4 async futures 125 milliseconds apart. The exact numbers don't matter. You could do 3, you could do 2. What matters, though, is that it's more than 1. And this creates essentially a virtual clock that's resilient to that client 1 pausing. So let's do an example where client 1 sends a request to a stateful service. The service actually responds, but because that client was garbage collecting when it was responding, a naive timer would incorrectly throw an exception when it wakes up from the garbage collection. Contrast that with our GC-tolerant timer, which correctly returns the result and does not pollute our logs with an incorrect error that misleads our investigators. Before we implemented this, we spent a significant amount of time tracking down services that thought their data stores were slow, when in reality, their caches were actually quite fast, their key value stores were quite fast, but their service was under load. So this technique doesn't, again, make the problem go away, but it does help you resolve it faster by preventing your operators from getting distracted. And then finally, sometimes things are going to break and you're going to get load shedding. And when that happens, we do allow a retry against stateful services. We allow really just 1 retry, although it is implemented generically to more than 1. We use a slightly modified capped exponential backoff algorithm. The only real modification that's worth pointing out here is that the first retry happens relevant to that SLO target. So you can see how having those SLOs is allowing us to more intelligently retry against our backends. If we didn't have those service level objectives, then we would have to take something that would probably mess up with our SLOs more frequently. But wouldn't it be nice, though, if we didn't send any requests to that slow server in the first place? That's where load balancing, or I like to say load unbalancing, comes into play. So at the bottom here, we have a bunch of resources about different load balancing strategies, including a simulation where you can reproduce these numbers. But the end result is that the typical load balancing algorithms, like random load balancing or round-robin load balancing, they don't actually work very well at avoiding slow servers. Instead, a lot of people at Netflix use choice of two, the power of two random choices. And we've actually recently rolled out at Netflix an improvement on choice of two called weighted choice of n. And the way that works is by exploiting a priori knowledge about networks in the cloud. So specifically, this is 3 zones in US East 1, and those are the latencies between them. We know that because we have a replica of data in every zone, if we send the request to the same zone, we're going to get a faster response. We don't need anybody to tell us that. We know it. We can measure it. So all we have to do is kind of weight requests towards our local zone replica. But we want this to degrade naturally. So like, what if we only have 2 copies? Or what if we are in the wrong zone, etc. So instead of just having like a strict routing rule, we take our concurrency, and instead of just picking the 2 that have the less concurrency, we weight the concurrency by these factors. So this sounds pretty cool. Does it work? Yes, it works really well. So this is an example of us running a synthetic load test where we took a Cassandra client that was doing local 1 reads, and we moved it from our weighted least load balancer algorithm to the out-of-the-box choice of 2. And immediately we regressed from 500 microsecond latencies to 800 microsecond latencies. I'll point something out. That's client-side latency. That's sub-millisecond latency from a database client to its server. This looked pretty positive, so we were like, we should put it in production. And we saw a bunch of graphs like this, just dropping off a cliff. And this is fantastic. We love it when our theory matches our measurement, matches production. And if you're curious to learn more, we talked about this at ApacheCon last year, and I've left links at the bottom. All right, so let's put all these techniques together. And let's look at a real-world key value service issue, which did not turn into an incident. So at time t1 at 7:02 a.m., an upstream client of this key value service suffers a retry storm, and their traffic instantly doubles. Within 30 seconds, our additive increase, multiplicative decrease server concurrency limiters are shedding load off of the server, trying to protect the backend from the sudden load spike. Meanwhile, those client hedges and exponential retries we talked about are mitigating the impact. This is such a small impact that nobody's even we're not violating any of our user visible SLOs at this point. The only problem that we have is that high latency impact. And that's because we went from 40% utilization to 80% utilization in 10 seconds. So finally, our server autoscaling system restores our latency SLO. And this whole process, from the client load doubling, to our server limiters tripping, to our client hedges and exponential retries mitigating, to the server autoscaling finally restoring the SLO, takes about 5 minutes. And there's no human involved here. Everything happened as expected. We had an issue, we mitigated the impact, we recovered quickly, no human was involved. All right, so I made a pretty important assumption when I was talking about hedging and retrying and breaking down work. What was that assumption? I assumed that the work was idempotent. And that's actually pretty tricky to build into your stateful APIs. I also assumed that your stateful APIs provided a fixed unit of work capability. Both of those have to be designed into your stateful APIs. So let's see how that works in the real world. And we'll motivate it with 2 real-world production examples in our key value service and our time series service. Now hold on, there's some code coming. It'll be okay. We'll walk through it. Let's assume you have to retry. How do you make your mutable APIs safe? Well, the answer is idempotency tokens. Who here has used Stripe to charge a credit card? A couple of folks. The way that works so that you don't double charge your credit card is using an idempotency key. the client generates a unique ID that associates with that transaction. So even if the device has to retry it multiple times, you don't have multiple charges. In concept, this is pretty simple. You generate some token, you send it with your mutative endpoint, and then if something bad happens, you just retry with the same idempotency token. But you have to make sure that the backing storage engines implement this idempotency. So let's dive in and understand what kinds of tokens we might need. In Netflix, an idempotency token is generally a tuple of a timestamp and some form of token. Depending on the backend, these things are going to change. So let's look at the simplest one. At Netflix, we use a lot of Apache Cassandra. Apache Cassandra uses last write wins to duplicate things. So as long as we send mutations with the same timestamp, they will deduplicate. So we can use client monotonic timestamps, in this case, a microsecond timestamp with a little bit of randomness mixed into the last character just to prevent a little bit of duplication, and a random nonce. And the combination of this UUID4 and the timestamp uniquely identifies that mutation. If we have a more consistent store, we might need to make a global monotonic timestamp within the same region. Perhaps we're like reaching out to a Zookeeper cluster to acquire some lease, or perhaps we're using a store like FoundationDB, which has a central timestamper. And then finally, the most consistent option is to take a global transaction ID. This is how a lot of transactional data stores work. For example, like MySQL or Postgres, where they actually associate a global transaction ID with a mutation. And you have to somehow encapsulate that transaction ID or move it into your data model so that you can retry against those stores. Transactions don't magically make your database isolated or idempotent. You have to actually put it in your data model and think about, I might have to retry this write. How would that look? But these three different options have a different consistency reliability trade-off. So on the x-axis here, we have kind of the level of how strongly consistent we are, ranging from not at all consistent all the way up to global linearizability. And on the y-axis, we have the reliability of that technique. And we'll notice that the regional isolated tokens and the global isolated tokens have problems. Now, why do I say that they're less reliable? It's because they require communication across the network. A client monotonic clock requires no network connectivity for you to generate the next token. Contrast that with a local region token where you need at least a quorum in a region to vote, or a global one where you have to talk across a WAN network. So at Netflix, we tried as much as possible to have client monotonic clocks. I think an earlier presenter said it really well. If you can make it less consistent, make it less consistent. Nobody knows if the recommendations in Netflix are the right recommendations in Netflix. So don't bring down your service trying to get a global linearizable clock to use in your transactions. I am going to be a little bit contrarian though, because earlier we heard about how clocks are problematic. And if the clocks are outside of the cloud, I agree with that. However, we actually measured this across the Cassandra fleet at Netflix, over 25,000 virtual machines, across over 20 instance families, all with Nitro cards in them though. And we did not observe clock drifts beyond 1 millisecond. The only time that we observed clock drifts above 1 millisecond, non-monotonic, was when VMs booted. So the first about 2 to 3 minutes of a VM's life, it has an inaccurate clock, and then after that, it's accurate. How does this work? Atomic clocks. It's pretty cool. So EC2, in every availability zone, maintains a highly accurate clock source, and then using their Nitro system, they give your VM direct access to it. And I should say that when I set out to write this memo, it was because the Cassandra community was proposing using clocks in a strongly consistent method. And so I was like, no, everybody in distributed systems know that clocks don't work. And then we measured it, and it turns out they actually work pretty well. Surprising, unexpected, but it turns out accurate. I highly encourage you, if you are building a system based on clocks, measure it, see what happens. All right, so we've seen the concepts, but how does this actually work in reality? Let's dive into some examples of real-world APIs using these concepts. We're going to start with the key value abstraction, which at Netflix offers developers a stable hash map as a service, a 2-level hash map, and exposes a pretty simple CRUD interface. You can write items to the store, you can delete them, you can read them, and then you can scan all of the items across the entire outer map. So let's dive in. Let's look at put items. We can see immediately the idempotency token pops right out. The first required argument to write data to the store is you have to have an idempotency token, generated via one of those methods that we talked about earlier. But we also see that in our list of items, there's a chunk number, and that facilitates the clients splitting up large payloads into multiple small ones, and then followed by a commit. On the read side, we see the same kind of breaking down of work. A getItems response does not guarantee that you will receive 1,000 items or 2,000 items. Instead, it attempts to return a fixed size of data. And this is because we want to be able to retry each component. Now you might say, gRPC, shouldn't you be using streaming? That's what we thought too. It didn't work very well. And the reason it didn't work very well is because all of those resiliency techniques I talked about, where you can retry individual pieces of work, and you can hedge, and you can speculate, and you can retry, they don't work in a streaming API. So instead, we've shifted almost all of our stateful APIs to paginated APIs that return fixed amounts of data. And then the client has to explicitly request the next page. This also has nice backpressure effects, where the client, if the client isn't asking for the next page, the data store does not preemptively return it. This does lead to one interesting failure mode, though, which is that because most storage engines implement pagination based on number of rows, and we want to implement pagination in terms of size, we have this mismatch, where the server might do many round trips to the data store in order to accumulate a page. So many round trips that we actually bust the SLO. But that's pretty easy, because we know what the SLO is, so we can just stop paginating. At no point did our API promise that we would return a fixed amount of work, or that we'd perform a fixed number. So instead, we'd rather present progress to the client, and then let the client request the next page if they need it. In many cases, they're just asking for the first item. Finally, let's look at scan. Scan is just like get, except that there's no primary key. And the only kind of interesting thing in this API is that when you initiate a scan, the key value service dynamically computes how many concurrent cursors it releases to that client. And that's the repeated string value next page. So for example, if the backend system is lowly loaded, then it might return a high concurrency, like 16 concurrent cursors, that then the client could consume quite quickly. If a lot of clients are scanning, then it will only return a small number of cursors. And this has a natural backpressure effect, where if a bunch of clients show up and start full table scanning this namespace, the key value service protects itself and rate limits how quickly they can scan. All right, so let's wrap it up. How do we put it all together? Well, on the right side, we saw that item potency token in use to deduplicate. In this case, the backend is some storage engine that implements a last rate wins use case, so the timestamp is sufficient. We are able to chunk and break down large writes. And on reads, we return pages of work within the service level objective. We do not offer a service level objective across all pages, because at least at Netflix, people can store gigabytes in a single key in our key value store. We can't offer an SLO on how quickly we'll return gigabytes. We can offer a throughput SLO, which is a proxy for that individual page size limit. So like if you take that size and multiply it by the number of pages, that's your throughput SLO. And I think a key insight here is that we're focusing on fixed size work, not fixed count work. As we mentioned earlier, every byte that we transmit, either in writes or in reads, is an opportunity for failure. All right, let's see. So that's like a nice example. You might say, oh, that's like, that's just one key value API. What about other APIs? It turns out you can use these techniques in general. For example, at Netflix, we have the time series abstraction. This stores all of our trace information, PDS log blobs, which are like playback log blobs that tell us that somebody hit play. And just to kind of like demonstrate the scale of this service handles between 20 and 30 million events per second, fully durably, with retention for multiple weeks. And that's how the customer service agents know that your TV had that really odd error at 2 in the morning while you were watching Bridgerton. So how does the system work? Well, we have our write event records endpoint, which takes a list of event records. And nowhere in this event record do we see an item potency token. But I promise you it's there. Just look a little closer. On the read side, it looks just like the get items. We have get items on the top and we have scan on the bottom. Essentially read a specific event stream or read all of them. The item potency token in this service is actually built into the contract of time series. Specifically, if you provide an event that has the same event time and the same unique event ID, then this backend storage of this deduplicates that operation. So while it's not called an item potency token, it's using the same concept. And on the read side, again, we see that breaking down of a potentially very large response into multiple pages that can be consumed progressively. And the one thing that I'd like to touch on this service is that because of the massive scale here, developers asked us for an additional level of reliability. And they were willing to trade off significant amounts of consistency in order to get it. And specifically, that's that operation mode on the left there, which we call fire and forget, where the only thing that the time series client does is like enqueue it into a buffer and goes like, okay, I'm done. It doesn't even wait until it gets off the box. Is this durable? No. Would most database people say that that is like an acceptable thing? Probably not. But our users really loved that that could handle 20 million writes per second, and it worked all the time. They didn't care if we dropped like one service trace out of billions in that minute. But then we do offer more consistent and less reliable options as we go to the left. For example, we can say, we'll let you know when we have it enqueued into our in-memory queue on the time series server. Or we'll respond back to you once it is durable in storage. So we can see again how, depending on what your customers need, you can be more reliable by trading off consistency. Or if they needed that consistency, you could just spend a lot of money. That's another valuable way to get the type of reliability that you need. All right, so let's wrap it with time series. Again, we see the idempotency token on writes. We see multiple modes of acknowledgement. In this particular service, we just ban large events. Like you can't write large events to this larger than 4 megabytes. And then reads return with pages within the SLO. Fixed size work, not fixed count. All right, and with that, we've seen how we can make modifications to our stateful APIs to be able to use those client and server techniques that we covered earlier in the talk. And I hope that some of these might help you improve the reliability of your stateful services. With that, thank you. Please remember to vote and leave feedback.
Thank you. Any advice first in enabling technologies for the hedging and the weighted choice routing?
Enabling technologies for hedging? Weighted choice routing. It's a good question. I mean, I think that the generic answer would be something like a service mesh, because that would allow you to implement those techniques like once centrally in your proxy that does egress routing. You could implement your load balancing policy. That particular like weighted choice of n, that requires a little bit more metadata because we need to know information about like where data is stored. So it's a little bit more complex to make kind of generic, but you can do it. And then on hedging is very, very easy to make generic. You can throw that in service meshes. You can throw it in some generic IPC library that you distribute to all your clients. Hedging is easiest to implement in a language that has proper async futures, so like Rust or Java or C++ with futures. It's really hard to implement in something like Python, although you can do it. So that's one of the reasons why I think I would probably lean towards some kind of external sidecar that implements those resiliency techniques centrally. Does that answer your question? Great.
Hi, thanks for the talk. Do you have any strategies for the server-side handling of the idempotency tokens?
Yeah, great question. So many data stores have a built-in idempotency technique. So for example, Apache Cassandra does last write wins. So as long as you can present a mutation with the same timestamp. Other cases are more difficult and usually involve some form of data modeling. So for example, like let's say you've got a transactional SQL store, you could implement idempotency by doing a transaction like a compare and set operation. So insert this if it doesn't already exist. Insert if not exists is an idempotent idempotent operation. But yeah, it's definitely per storage engine. So if you're using like Elasticsearch, the way that you implement idempotency for Elasticsearch is different from Cassandra, which is different from like Postgres. Does that answer your question, or would you like more examples?
Yeah. Handle it at the actual data store layer as opposed to the service layer itself.
Yeah, so that's actually one of the reasons why Netflix has been moving towards these online stateful abstractions. So like the key value and time series abstraction that I presented, one of their core reasons of being is to implement those idempotency techniques for people. So like when you send mutations to the key value service or to the time series service, it handles like, oh, I'm talking to DynamoDB. This is how DynamoDB does idempotency. Oh, I'm talking to Cassandra. This is how Cassandra implements idempotency. Although you certainly could do that in like libraries. I just think it would be more difficult to maintain.
Thanks.
I think we've got a question in the front.
You mentioned decommissioning some couple thousand servers a month or a year.
A year.
In AWS, that just means you give them back, right?
Yes.
I was curious whether you like communicate that to AWS, or you just leave it for us to consume or something.
It mostly comes back to us, actually. This is a great question. And the first technique that we use is that we detach but don't terminate yet. And then we allow the autoscaling group. So from an autoscaling group, we detach the instance, but we don't terminate it. That kind of reserves it out of the pool. Amazon gives us a new instance, which hopefully is healthy. And then we release that one. And then to answer your question of like, do we just leave it to the plebes? It just goes back into the pool. The pre-flight checks help us not get it back. This is especially a problem for like narrowly constrained instance families. So for example, back when like we used a lot of D2s, it was very common for us to get the same D2 back. And so those pre-flight, that's actually why we added the pre-flight checks, because the pre-flight checks on our end will reject that hardware from re-entering the fleet. There's no, as far as I'm aware, there's no durable way to know that a new Amazon instance is an old one. So like if you have one instance ID and then you terminate it and Amazon hands you back a new one, I'm not aware of how to know that it is degraded. We have talked with AWS about how to improve these communication capabilities. It would be nice if they had an API where we could be like, our monitoring systems have detected this degraded hardware. One thing I can say is that EC2 actually already knows a lot of times that that drive is degraded. They just can't pull it because there's a user workload on it. So think about it like from their perspective, they don't know if you're using the drive. Like they might know that it's throwing all these IO errors, but they don't know if your workload cares about that. So they're not gonna just like turn off your workload. Yeah, I think in practice, I don't think I can share the exact numbers. I can talk to you afterwards, but in practice, Amazon actually catches a lot of that on their own. Does that answer your question? Yeah. Fantastic. All right, I think there's a hand in the back.
Hi. You were talking about designing API and designing clients and well, this is SDK, right? So are you usually providing like a set of API to the users of the stateful services, or they can use stateful services directly? How the relationships usually work?
So we target an 80-20. So about 80% of services at Netflix go through those abstraction layers, in which case we offer them a lot of guarantees around API compatibility. About 20% of users do go directly to storage engines, in which case we like send them the 25-page memo and like, this is how you implement idempotency, this is how you don't kill this data store, this is how you do backups. Like, but a lot of folks do want that level of control at Netflix, and so we do give them that freedom. Although it is, again, an 80-20. So about 20% of users do direct data access and manage their own implementations of some of these. We do provide data store client libraries as well in all major supported languages. But yeah, we definitely kind of push people towards the APIs that we know have all the idempotency and resiliency techniques that we think are important. There are cases where, for example, we've worked to get some of these resiliency techniques. I'm actually working with a colleague right now to get that load balancer into the open source Cassandra driver. So we do sometimes, bring that back to the open source community, but it can be challenging because a lot of these techniques, when you don't have a requirement for really high reliability, a lot of them don't make sense to pay the engineering complexity. I think there was a speaker earlier who alluded to like NASA, right? So like NASA, it makes sense for them to invest in reliability. If you're showing cat pictures, maybe it doesn't. I hope that answers your question. All right, fantastic. Thank you, everyone.